and find out why that happened to you. And the reason that happened is when you turn crossfeed on, the FCF relay is activated, and that pulls this whole bar of switches all the way across and then activated that particular relay at the top, which was the TCO relay. See? Nothing to it. All right, now let's cover just a last couple items about electricity. And before we do that, before we take off and do these new items, I want to point out to you that the way that I think is easiest to answer all these questions is when they ask you on the test, get a pencil and paper and make a chart and say, what would happen if the power was normal? And you make a list of all the relays and say, would they be activated? For instance, if the power is normal, the LTS relay would be activated. And the answer is no, it would not. That was supposed to be a question. And if the power is normal, would the RTS relay be activated? And the answer is no, it would not. How about the FCF relay and so on, all the way down through? How about when power is on the right tank? Well, would the LTS be activated? No, because L stands for left. How about RTS? Yes, because R stands for right. And you begin to get a pattern here. And so left, right, fuel cross-feed and all of that, you'll begin to understand what all these relays mean. So when you get on the test and they ask you this question, by the way, I'd put this question off to last because it's going to take a long time to answer. And I would get the easy ones done first because they're all weighted the same. But in any event, I would make up this table, and we've got the table in the book so you can practice on it and see what relays are going to operate when, and then you can answer the questions. Now here is an electric motor that could occasionally overheat. Now, what is the desirable thing when an electric motor overheats? Well, the desirable thing is this. You have a thermal switch in the electric motor that breaks the circuit and prevents a fire. That's the desirable thing, and that's what they tell you will happen on the test, that when an electric motor malfunctions and overheats, it can incorporate a thermal switch that will break the circuit. Now, that's logical, and speaking of logical, let's talk about a new subject, and that is called logic gates. Logic gates are circuits that you can use to pass on information, and they're based on the idea of binary mathematics. Binary mathematics means you can have either 1 or a 0. Something has either got a charge on it or no charge on it. If it has a charge on it, it's a 1. If there's no charge on it, it's a 0. And you can use that system to pass on information. And this is a logic gate, and here's the way it would work. First of all, you have an input, and each input can have either a charge on it or no charge on it. And if a certain condition satisfies the requirements of the circuit, then information can be passed out here. If this is true, then I'm going to turn the charge on here and put an output here. This particular logic gate we're showing right here is what is known as an AND gate. Because what happens is, in order for there to be an output charge out here on an AND gate, in this particular case, what you have to have is all three of these be true. There must be a charge here, and here, and here. And if all three of those are true in this particular case, then you would have an output here, and that is what is known as an AND gate. So all three of them have to be true. Now, they're going to ask you a question about this on the test, and the question they're going to ask you about it on the test is, if you had this logic gate depicted and you had an output of 0, what would be the case? How would that get to be that way? And the answer is, in order for there to be a 0 output, you must have one of these not have a charge on it. Because in order for there to be an output, you have to have all three have a charge on them. That's called an AND gate. Now let's take a look at what is known as an OR gate. And an OR gate, you might notice, has the shape of a boat. And if you have any trouble remembering that this is an OR gate, remember that boats have oars. And I am so sorry. That's the way it works. You're going to remember it now for the rest of your life. Now, here's a case of an OR gate. And what we're saying in an OR gate is, if any one of these inputs has a charge on it, then there will be a charge out here. There will be an output here. And once again, what we're talking about is an integrated circuit that says if any one of these is a yes, then the answer out here will be a yes. And we're doing this with electrical charges. And that is an OR gate. And they're going to ask you, what is the relationship between the inputs and outputs of this particular OR gate? And what it says is any input being a 1 will give you a 1 output out here. Now let's do another one. Let's take a look at what is known as an exclusive OR gate. An exclusive OR gate looks like a boat with a trailer behind it. And an exclusive OR gate says that in order to produce a 1 output, it has to have these two inputs be dissimilar. They have to disagree with each other. And anytime they disagree with each other, then there will be a 1 output out here, and that's called an exclusive OR gate. Now let's take a look at the question they're going to ask you about this on the test. They're going to show you several of these, and they're going to say which one of these is an exclusive OR gate. Well, what you do is you take a look at it. You know that the inputs have to disagree with each other. Well, this input here, the inputs don't disagree with each other. Here they disagree with each other, and the output is a 1. So that is an exclusive OR gate here. Here, they disagree with each other, but the output's a 0, so that's not a properly operating exclusive OR gate. So number 2 on this figure is a properly operating exclusive OR gate. And this is basically an integrated circuit to do this, and it's just a way of conveying information. Now, integrated circuits, as you know, often contain transistors, and it would be helpful to you on the test to understand how a transistor works. Here's a whole bunch of different kinds of transistors, but let's take a look inside a transistor and see if we can figure out how they work. Now, transistors, as you probably already know, are made of silicone material that are doped with another kind of material to change the characteristics of the silicon. And if they're doped with a certain kind of material, it's called, the silicon material becomes N-type silicon material. And in that particular case, N-type material has lots of free electrons in it. And P-type material, if it's doped with another substance, it becomes P-type material. And P-type material has lots of holes in which electrons can go. And you can use this information because you can construct an amplifier or a device to control the amount of current that flows through the transistor. And here's the way you'll do it. Let's assume that you have a transistor that's composed of N-type material here, P-type material here, and N-type material there. It's often referred to as a sandwich. And this is the junction between the N-type material and the P-type material. And that's a very important concept right there. Now, what you have to have is certain circumstances for current to flow through here, and here's what the circumstances are. Let's assume you put a negative charge over here, and let's assume you put a positive charge over here, and on the base, we're going to call this, by the way, the emitter, where there's a negative charge, because electrons are going to flow from the emitter through the base to the collector. And in order for current to flow, we need a negative charge here, a positive charge here. In order for current to flow, we also have to have a positive charge here, and here's why. If you put a negative charge here, what you're going to do is drive all the free electrons to this end. If there's a positive charge here, that means there will be holes available for those free electrons to flow, and electrons can flow across this junction. If, on the other hand, it was the other way around, let's assume you had a positive charge here and a negative charge here, then the electrons would be driven away from the junction in the holes, and the electrons could not flow across here. So in order for electrons to flow across through a transistor, the base has to have a different charge than the emitter. The emitter has a negative charge here. The base will have to have a positive charge in the case of NPN type of transistor, and then electrons will flow across. So this is an NPN transistor, and when this has a negative charge, that's the emitter, and the base has a positive charge, the junction is called forward biased. And forward biasing means that electricity will flow, a current will flow through the transistor. Now, another kind of transistor you might have would be, instead of an NPN transistor, would be a PNP transistor, and it's forward biased when the base is negative and the emitter is positive. And you can remember that because that's N, negative, and that's P, positive. And that's how you remember it. So in order for a transistor to conduct electricity, it has to be forward biased. And on a PNP type of transistor, it's forward biased when the base is negative. So the middle of this sandwich is called the base. The part that sends off the electrons is called the emitter. And the part that you might think of as catching the electrons is called the collector. Now let's take a look at some questions they're going to ask you about that. And to do that, let's take a look at figure 22. And figure 22 is the symbol for a transistor in a schematic drawing. It's a symbol you would use in a schematic drawing for a transistor. And here we have a collector over here, and we have a base, and we have the emitter. Now notice the base is more positive than the emitter, and that's what you have to have in order for current to flow. And by the way, even though we said the electrons flow from the emitter to the collector, current is different than electrons. Just a matter of convention, you say that current flows from positive to negative. We know electrons flow the opposite direction, but when you're talking about how current flows, it's said to flow from positive to negative. So this is a properly biased transistor right here because the base and the emitter have opposite charges from each other. Now let's take a look at the question they're going to ask you about this on the test. And the question they're going to ask you goes like this. They're going to show you these three and say which one of these has current flow. And it's properly set up transistor for current flow. And we've already said it's number 1 because the emitter and the base are opposite each other. And remember, current is always said to flow from positive to negative. So this is out because they got the current flow in the other direction. And down here, we have a negative base and a negative emitter, and that won't work. It's not forward biased. So drawing number 1 is a transistor that will allow current to flow. Now let's take a look at figure 23, and let's take a look at another question we're going to ask about electrical things involving a transistor, because here is a transistor right here at this point. And let's back off just a little bit more so that we can see this light up here, because what we're trying to do is light that light up there. And what we're finding is that we have a negative ground here, and we have a battery over here with positive over here. And when we have current flowing through this whole assembly, we're going to light that light up there. Now let's take a look at it. We have here a transistor, and when there is a positive charge on the base, current will flow, because here we have a negative emitter, positive base, and a positive collector. So when there is a positive charge on the base, current will flow and the light will light. Now let's take a look at what we have here. We have here a rheostat, and we can tap off this resistor anywhere here, and if we tap off up on this direction more towards the positive pole of the battery, then we'll have a positive charge. If we pulled off down here, we'll have a less positive charge on the base. So we can control the amount of positive charge on the base by where we tap off. If we tap off closer to the positive pole of the battery, then we would have a positive charge on the base, current would flow, and the light would light. Now, a couple questions they're going to ask you. First of all, what would happen if you had an open here, and instead of having R1 shorting the ground as it does, you just had a complete open? Well, if you had a complete open, that you wouldn't have this flow to ground, and therefore you would have a very positive charge on this base, and what would happen is current would flow all the time. So the light couldn't be turned off. So if you had an open here at R1 instead of being a conduction to ground, if you had an open, then the light would be on all the time. You couldn't turn it off. Now, what would happen if R2 stuck in the up position? Well, the same thing would happen. The light would be on full bright because if you had R2 stuck in the up position, what happened is you'd move that tap on the rheostat closer to the positive end of the battery, and the light would be on all the time. So you can see now that being an A and P, it does make sense to understand transistors, because at least they're going to ask you this question on the test, and therefore you need to answer it on the test. And believe it or not, you and I have just covered everything that they're going to ask you about basic electricity on the A and P general test.